Hello guys! Finally I have a small setup of an electronics lab with a power supply, DSO, soldering station, TMM and many more things. Come on guys, I have already invested this time and money. Then why don't you hit that subscribe button as well? And for Hindi crowd in the house,
मालिक अब इतना खर्चा हो गया
तो एक सब्सक्राइब का बटन दबा ही दो.
एक उसको भी दे, उसको भी दे.
We have to reach the 50k mark as soon as possible. Well, in one of the last videos, we saw about the edge bridge motor driving technique. And now this time, we're actually going to see the working of the edge bridge driver with a real circuit because, why not? I told you last time only that some interesting things are coming up. If you haven't already seen the previous video of edge bridge, then I suggest you to watch that video first. You'll understand this topic more easily. But if you are a lazy engineer like me, then don't worry. We'll try to cover up as much as possible. So, let's start. The edge bridge, also known as a full bridge, is a switching network consisting of 4 control switches, which are MOSFETs, and is capable of creating a bidirectional current and reversible voltage across the load. The load is nothing but a DC motor. This circuit drives the motor. Well, we can even change the speed of the motor with this. It comes in handy while driving a motor because it allows a change in the direction of its rotation. The motor is connected at the junction of these MOSFETs. To rotate a motor, the MOSFETs are switched on and off, and we can provide a PWM signal to the MOSFET having a constant frequency, so that the average voltage across the MOSFET will vary. And because of that, we can change the speed of the motor. The MOSFETs in an edge bridge can be switched in different sequences to provide the desired voltage polarity. We can switch 2 MOSFETs at a time to change the direction of the motor. Let's take an example of this circuit. These MOSFETs are Q1, Q2, Q3 and Q4. When Q2 and Q3 are turned on, the motor runs in the forward direction. Whereas when Q1 and Q4 are turned on, the motor rotates in a reverse direction. Let's see the working of the edge bridge motor driver. This development board is provided to me by the Nextplayer team. Just like our explanation, here are 4 MOSFETs: Q1, Q2, Q3 and Q4. Well, the idents are different, but don't worry, we'll follow our pattern. Here we have applied DC supply to the circuit, and I have connected a DC motor at the output to check if this circuit is properly working or not. Let's turn on the supply. The input is around 13 volts. Cool, the motor is rotating. Now I will change the direction of the motor and boom, motor is running in the reverse direction. Haha, magic. I can even change the speed of the motor with one touch of a button. Well, you must be wondering, only these 4 MOSFETs are sufficient to drive the DC motor. Then why this board is so big and what are all these circuits? Are these even useful? Well, let's go to animation again. To control these 4 MOSFETs, we need a control circuitry. Well, that is self-explanatory. Also, to control the speed of the motor, we need to provide a PWM. What do you think all of that is coming from? Let's see the overall block diagram of the edge bridge control circuit. It is made up of an input power supply, clock, PWM generator, a driving circuitry for the MOSFET, and edge bridge network. Along with that, there is a closed loop of overcurrent protection. Let's see the significance of each block. This power supply section can accept input from 12 volt to 48 volts. That's why we don't have to worry about over voltage till 48 volts. This power supply gives a constant output of 12 volts and 5 volts after that. This 12 volt is given by a buck converter and 5 volt is given by a linear regulator. These 12 volt and 5 volt signals are required for the internal control circuits, which we'll see in some time. This section has transient protection and reverse polarity protection. So even if I interchange the positive and negative supply wires, there won't be any adverse effect. The clock is basically a frequency and duty cycle generator. It has a 4 MHz crystal oscillator. This block gives us variable duty cycle which can be controlled by using the switches. Now the PWM section controls the dead time function and enables PWM. Well, the direction of the motor is also taken care by this block. The driving circuitry is made up of high side and low side drivers to drive 4 MOSFET of the H bridge. Out of these 4 MOSFETs, the Q1 and Q2 are high side switches. And we already know it is very hard and complicated to switch a high side MOSFET, especially when there is an N-channel MOSFET. So there is a different type of high side driver in this circuit called charge pump to supply high side MOSFETs. Don't worry, we are going to check each and everything. Next is the H bridge network. With that, it has decoupling capacitors, a snubber circuit, gate drive resistors, and current measurement circuit. Overcurrent protection is very helpful. Let's say by any chance, the current of the H bridge circuit goes beyond a certain limit. Or if there is any short circuit, then this particular block will switch off the H bridge. Now I'll try to explain how the H bridge of this development board is working in very easy words. We provide PWM to MOSFET Q1 and Q3, which means those will be continuously switching to control the speed. The MOSFET Q2 and Q4 will be continuously on. These MOSFETs would be responsible for motor rotation. We know that if Q2 and Q3 are turned on, then this motor will rotate in a forward direction. So Q2 will be on continuously and will provide PWM to Q3. Now, if you want to turn the motor in the reverse direction, then we just have to turn on the MOSFET Q4 fully and provide PWM to MOSFET Q1. That's all. Well, we have already seen in the last video that there are 2 different types of H bridge motor driving techniques, which are bipolar and unipolar drive. If you have watched that video and remember some concepts, then you can tell me in the comment section which type of driving technique is used in this circuit. Anyway, you'll get the answer to this question at the end of the video. Well, enough of the theory. Let's check the circuit again. This is the power supply section with buck converter. This is linear regulator, overcurrent protection circuit. This is the low side and this is the high side MOSFET driving circuitry. This part over here is the clock and PWM generator circuit. This is the motor direction control circuit, and these are the switches to control the speed of the motor. One more important point here is that there are no microcontroller and application specific ICs used in this whole circuit. It is solely made up of discrete components such as transistors, logic ICs, diodes from Nexperia, and some resistors, inductors, and capacitors. You know, Nexperia has an awesome portfolio of transistors such as MOSFETs and BJTs, as well as diodes and logic ICs. I use their components in many of my circuits. Now we'll check the MOSFET gate signals and verify whether the working of the circuit is as expected. I turn on the scope, multimeter is on, all things are connected properly. I have all the test points out here. We need to check all the gate signals of these MOSFETs Q1, Q2, Q3 and Q4. Test point 39 is nothing but the MOSFET Q1's gate. TP36 is connected to Q2's gate. TP40 goes to Q3 and TP41 is connected to MOSFET Q4. Now again, we'll power up this circuit. The motor is running and it is taking this much current. Let's see the output of the buck converter. Yeah, it's 12 volt at TP5. And the output of the linear regulator at test point 7, it is 5 volts. Cool. Let's see the gate signal of MOSFET Q2. It is high with a voltage of around 18 volts. So the MOSFET Q2 is on. If the Q2 is on, then Q4 should be off. And yes, it is off. Well, if the motor is running, that means Q3 should be turned on with PWM. Let's see that as well. Cool, we can see the PWM across Q3. As I change the speed of the motor, the pulse width is also changing. If I increase the speed, the duty cycle increases and at last Q3 turns on fully with maximum motor speed. If I decrease the speed, the duty cycle decreases to a minimum and eventually the MOSFET Q3 turns off and motor stops rotating. Let's see the reverse motor rotation by just flipping the switch. Now we'll see the gate signal of MOSFET Q4 at TP41. It is high. As it is a low side switch, its gate voltage will be low. So the Q4 is on. If Q4 is on, then Q2 must be off. And yes, it is off. Well, if the motor is running in the reverse direction, that means Q1 should be turned on with PWM. Let's see that as well at test point 39. Cool, we can see the PWM across Q1. And its voltage is around 21 volts with respect to ground because it is a high sweat switch. Again, if the speed changes, the duty cycle of the PWM changes with respect to speed. Well, that's how an H-bridge motor driver works. Oh yeah, coming back to the question. The question was which type of driving technique is used in this circuit. If your answer was unipolar driving technique between bipolar and unipolar drive, then congratulations, you were right. We are going to check each and every block of this board and its circuit in detail, such as this buck converter, driving circuitry, and many more. So stay tuned. I hope you got something from this. If you have any questions, you can write them down in the comment section. Please don't forget to subscribe to my channel. And finally, thank you so much for watching this video.